The Michelson Postdoctoral Prize is an international award given annually by the physics department at Case Western to an outstanding postdoctoral researcher in any subfield of physics. Because of the exceptional past nominees and prize winners, it's become a leading award for early career scientists. Audrey Bienfait is the 23rd recipient of the Michelson Postdoctoral Prize. And I'm now going to invite Professor Starkman, Distinguished University Professor and Chair of the Department of Physics, to introduce Audrey and to present her the award. So, Glenn.
Thank you, Hirsch. And I think we're going to start by presenting the award. That's right. So let me start by presenting the certificate. And congratulations.
Thank you.
And a little something that goes with it. And to thank you so much for being here with us this week and for presenting an extraordinary series of seminars in today's colloquium. And I did want to thank again the prize committee, which Hirsch chairs, consisting of Walter Lambrecht, Jesse Berezovsky, Kurt Hinterbichler, Edith Zahavi, Mike Kinchevsky, but especially Hirsch, I know, puts an enormous amount of work into this, as do all our staff who do all the printing of posters and organizing of food and travel and everything to bring Audrey here. Okay, so Audrey Bienfait did her doctoral work at Université Paris-Saclay and was then a postdoc at the University of Chicago at their Institute for Molecular Engineering. She is now a faculty member at the École Normale Supérieure in Lyon. And in her career, she has already had what the committee called 2 home runs. One of them having to do with entangling quantum mechanical circuits using sound, and the second in improving the sensitivity of MRI-like measurements for electron spins by 4 orders of magnitude. So we are very excited to have her as our Michelson Postdoctoral Prize lecturer this week, and to invite her to give her colloquium today about interfacing quantum microwaves to spins and phonons. Please join me in welcoming Audrey Bienfait.
Okay, well, first I would like to thank, all of you for coming, and there's a committee, Arsh. It's really fantastic to be here. Everybody that has hosted me has been very welcoming, and it more than make up for the amount of work that went into these 4 talks. So I will just move on to the colloquium now. Yeah, thank you very much. So this is about using quantum microwaves, and these quantum microwaves it's been now 10, 20 years that we have been able to really manipulate them using these quantum microwave circuits. And the story I wanted to tell you today is how we can really harness them to go and probe other type of quantum system with them. So it's in 3 parts, very simply. I just wanted to maybe give you a flavor on how we can make these electrical circuits quantum, how we can really control these quantum microwaves. And once I've explained that, how can we harness them to detect spins with a very high sensitivity, and then how we can also use them to probe matter waves or phonons. And really, don't hesitate to stop and ask questions. So if we go towards making electrical circuits quantum, then we have to consider a simple electrical circuits. So it's back to basic electricity for everyone. So we can take an inductor in parallel with a capacitor. You can derive the voltage and current relation for both. And when you solve the circuit, you will find that this is the LC resonator, harmonic oscillator, whose frequency is given by the invert of the square root of the inductance product the capacitance. You can relate it to a mechanical oscillator, where the flux in the inductor and the charge on the capacitor plays the role of the position of momentum, or for example, of a pendulum. And to to give some kind of reference for the type of electrical circuits that we are using, their frequency are between 3 to 10 gigahertz. Their impedance, that's say the square root of the inductance over the capacitance, range from 10 ohm to 110 kilo ohm, and that's because we can easily reach a capacitive value between a few femtofarad to 2 picofarad approximately, and the inductor more range in the 100 picohenry to 10 nanohenry to give you some kind of reference. So because this is an harmonic oscillator, while it has also to obey the rule of quantum mechanics, and if we want to go to this regime where we can actually observe the rule of quantum mechanics applied to this simple oscillator, then we have to go in a configuration where there are no losses so that we can observe the rule of quantum mechanics applied to a system that is not correlated with the environment. So for these circuits, that means having circuits without losses, without damping, and for us, that means using superconducting material in their best configuration, so that's at low temperature, to have the best quality factors that they can reach. So some example of LC circuits, they can be, for example, implemented by lumped element. So for example, here you see a big interdigitated capacitance in parallel with a small inductive wire. Or you can also find coplanar implementation. So here this is a lambda over 2 or lambda over 4 transmission line. So both of these 2D configuration can host this kind of electrical modes. And because they are cooled down to approximately 20 millikelvin, they can reach quality factor about 10 to the 5, 10 to the 6, or similarly, a lifetime of 10 to 100 microseconds. So that means that one photon that would be stored inside could stay there for approximately 100 microseconds. So this is already maybe a long time to do some kind of manipulation, but people were unhappy with that. They tried to go to other, to better lifetime. And one thing that they realized is that here, the losses are mainly due to defects at the interface. And because this is a planar configuration, there is a lot of interface for the electrical mode. So what they did is to go to a 3D cavity where the mode is trapped inside a 3D volume, where now, for example, the walls play the role of the capacitor. And this really largely decreases the participation ratio of interface and so of losses to the mode, and thus allowed to improve the lifetime of the modes by a few order of magnitude. So this is already the first requisite to have this quantum microwave state, is to have no losses. So we have kind of fulfilled this criteria. The second one is if we take this harmonic oscillator in the quantum regime, one of the consequences of quantum mechanics is that the energy levels are quantized. So that's what you see here on this plot. Now, if we want to be able to address, control, manipulate the energy between this energy level on this ladder, we also need to be able to have this oscillator in an environment where the fluctuations are small compared to this transition. And so that means that the frequency of the resonator must be much smaller than the fluctuation given by the temperature. So we can very precisely quantize that. That's given by the Boltzmann statistics. And we see that the number of thermal photons that are put in by this thermal fluctuation is given by dissolution. So if I plot it as a function of the temperature for different frequency, you can see that there is a probability for the ground state to be occupied. I mean, the two are linked. We absolutely want to work in an environment where we would start with being in the ground state and not in a thermally excited state. So we want to go at low number of thermal photons. And if we work between 1 gigahertz and 10 gigahertz, that means working below 70 millikelvin, approximately. So that's what sets the regime for microwave circuits to be quantum, is both the fact that we need low losses, so superconducting materials cooled down at very low temperature, and the fact that we need to be much below the thermal fluctuation. And so that's where we are going to do our experiments. So now that we have these LC circuits that we can cool down and really think of them as a quantum object, we can try now to do something with them. It can't be an isolated object that we can't probe, because otherwise this is not experimental physics. We are not going to demonstrate any rules or principle of quantum mechanics with them. So we need to couple them to our instrument devices. And for that, we are going to exploit the fact that they have an inherent electromagnetic field. So the inductor generates a magnetic field, and the capacitor generates an electrical field that can be linked to the properties of the electrical circuit. So we can use this field to couple to other electrical circuits. But here, I would couple 3 quantum oscillators together. That's linear physics. And maybe linear physics is great and so on, but I find that we can do maybe a better job if we consider nonlinear physics. So we need also to be able to couple to other kind of quantum systems, so two-level objects that can be, for example, spins. So spins respond in a magnetic field, have energy level split by applying a magnetic field. And so because they are Hamiltonian, rely on the magnetic field, they are also susceptible to the microwave field that can generate an inductor. So it's possible to engineer a coupling between an electrical circuit and magnetic dipoles. Capacitor can generate the same for electrical dipole, and we can find that similar coupling exists to, for example, atoms or ions or other electrical dipoles. So we can also think of this dipole as simply two-level system, so that in the end it doesn't really matter whether they are magnetic or electrical, except when evaluating the strength of the coupling between the LC circuits and the two-level system. So if we start from the Hamiltonian for either the magnetic dipole or the electrical dipole and write the Hamiltonian of the system, we can figure out what is the interaction between the LC circuit and this two-level system. And we can also, by engineering the LC circuit, set this coupling strength and really engineered it. So this is characterized by frequency G, which is when coupling an oscillator to this two-level system, simply express the rate at which an excitation stored inside the LC circuit will swap to the two-level system. So you can see that this is called, this configuration is called cavity quantum electrodynamics. And because we are using, so that's for any kind of cavities and two-level system, but because here we are using circuits, we just rename it as circuit quantum electrodynamics. So this kind of, seeing this kind of interaction, that's to say having an excitation swap between one system and another, we can see that this is achievable only if the excitation resides in the system long enough to see a swap. So that's already give us kind of the scales that we need to have for this interaction strength to be visible and so to be in the quantum regime, kind of. And so we need to engineer this G. So we have these LC circuits. And now I'm going to show you how we can use also these electrical circuits to implement this electrical dipole and have large enough G to have coherence exchange. And that's implemented by a Josephson junction. So if we take an LC circuit and replace the inductor by a Josephson junction, the current and voltage relation for the Josephson junction means that the potential for the circuit becomes non-linear, non-harmonic, sorry, so that the energy levels are no longer evenly spaced. So that means that compared to the LC circuit, I will be able to address only a single transition. For example, the one between the ground state and the first excited state, without exciting the second excited state. So that means that will allow me to define a specific two-level system that has a specific transition that I can address. So this Josephson junction, it's very simple to implement. It's two metallic leads, two superconducting leads, separated by a nanometer scale insulating barrier, and that we generally create them by evaporation through a shadow mask. So we have just a little bridge of resist that is suspended, and we can evaporate on one side to deposit the first lead, oxidize the surface to create the insulating barrier, and then evaporate at a single angle to deposit the second superconducting lead. So that forms what is called the superconducting qubit. So that's an image of a superconducting qubit that we have realized at the University of Chicago. You can see that the big cross is the capacitor, and the Josephson junction is actually just at the bottom of the capacitor. You can see that there are also several elements that surround the superconducting qubit, and the goal is really to be able to control and read out its state. So it's cooled down at 10 milli-K before doing any of the experiments. So the first thing that you can see here is a superconducting resonator. And this is one of the implementation of this interaction between a two-level system and an oscillator, a quantum oscillator. And this is useful to determine what is the state of the superconducting qubit by sending signal in reflection on this oscillator, because the amplitude and the phase of this signal allow us to determine whether the superconducting qubit is in its ground state or excited state. So if we plot the quadrature of this signal on the polar plane, we can see that when the qubit is prepared in its ground state and we send the signal through, we have mainly the signal concentrated on one spot of the IQ plane. When we next prepare the qubit in its excited state and do the same kind of measurement, we have a measurement at another spot of the IQ plane. And this is not a resonant interaction I've shown you. It's a dispersive non-resonance interaction. And basically, what it implies is that the state of the superconducting qubit modify slightly the frequency of the superconducting resonator, and that's why the transmission measurement swap the spots in the IQ plane. So now we can divide to read out what is the state of the qubit when we do a measurement. We can just assign different regions of the IQ plane to a state of the qubit. So above the line, we are in the excited state. Under the line, we are in the ground state. So we can determine from that measurement, repeating several times, what is the probability for the qubit at the end of an experiment to be in its excited state or in its ground state. So that's the readout. But to perform this measurement, you have to be able to prepare the qubit in its excited state. So that is done by driving the superconducting qubit and prepare a specific quantum state on it. So that's to say any superposition of ground or excited state. So this quantum state can be represented on a Bloch sphere. So here I've put the ground at the bottom of the sphere and the excited state at the top. Any state that is an equal superposition of the two states is on the equator. And now the goal is to be able to prepare any kind of states that would lie on the surface of this Bloch sphere. So if I now apply a microwave drive nearby the qubit, I will drive Rabi oscillations on the Bloch sphere. So oscillation around the Bloch sphere, around an axis that is contained on the equator. So this is why this is called an XY drive, because it's a drive around an axis that is spanned by the X and Y axis of the Bloch sphere. So this allows to perform, for example, pi-2 and pi pulses, that's to say bringing the qubit from a ground to, for example, a superposition state, or ground to excited state by a pi pulse. So this is only a control over 2 axes. We can also introduce a third control by having not only a single Josephson junction, but 2 Josephson junctions in parallel. So this forms a squid. And if there is a DC line nearby that allows us to thread the flux through the squid, then we can control the relation of the phases of the 2 Josephson junctions. And so that can modulate the equivalent inductance of the 2 Josephson junctions in parallel. So this allows us to tune the frequency, the resonance frequency of the resonator, also of the qubit. And that allows us to introduce control over the z-axis. Because this block sphere is always taken with respect to a reference frame. And if we change the frequency of the superconducting qubit with respect to this frame, we'll either have the state of the qubit going more slowly or faster than the reference frame. And so that can lead to a dephasing, so rotation along z. So we have control over all 3 axes with this kind of electrical circuit. So the last thing that I want to introduce is what is the coherence of these superconducting qubits? How long can they keep their quantum state? So we can measure how long they can keep a photon by preparing them in the excited state with a pi pulse and watching how long they can keep this excitation. And we find that the typical time, T1 for them is approximately 20 microseconds, so that within the range of this whole field of microwave circuit, since the typical lifetime are about 10 to 100 microseconds. The second interesting time is how long a superposition state can keep its phase. So that's the phase coherence time, and we measure it via a Ramsey sequence. That's to say, first preparing the superposition state, waiting for a time t to monitor its decay, and then projecting it via another pi over 2 pulse to the measurement z-axis. And we find for our device that this has a typical time of 2 microseconds, which is pretty low compared to the standard of the field right now.
Sorry, just a clarification question. So you don't have an ensemble here, so presumably you just measure the same qubit over and over again?
Exactly, yeah. Yeah.
Is there an incredible number of measurements?
So I think here for each point, it's and there are many points, it's 1,000 measurements. Yeah. So I've shown you just a simple superconducting qubit, how you can read them out, how can you control their state, how you can monitor the quantum state that is stored inside. But this is really the building block for much bigger experiments. So a few of them are about performing quantum computing or the processing of quantum information. So that's a very large subject that is about associating, scaling up, putting together many of these superconducting qubits to really process information. So that's led by several academics group and a private company. I hope I put 3 dots because I was very worried of offending anyone. So this is, for example, the example from Google, which have announced a 72 qubit chip, and this is a picture of the cryostat where they cooled down this chip, and we can see that this is completely on another level of what I've shown you. But here, for the rest of the talk, I want to talk more about quantum sensing, which I would define for me as a way of using a quantum object either to measure other quantum objects or quantum properties or other properties using its own quantum properties. And I want to really apply it to 2 topics. The first one is how we can use these electrical circuits to detect spins, and the second will be about coupling to phonons. So why detecting spins? Why does it make sense to detect spins with electrical circuits? Well, then you have to think back about magnetic resonance, which is, in a nutshell, detecting the absorption and emission of microwave radiation by the spin. So, for example, this is an old image from a paper where this is one of the first time that they send microwave pulses that perform Rabi oscillation of those spins that finally led them to recover some coherence and emit some spontaneous radiation, so a spin echo inside the resonator that can be detected to infer the presence of the spin inside the sample. So it's a very useful technique. It's used in many biological or chemical biolabs and chemical labs, just using spin spectroscopy, electron spin resonance spectroscopy. It can also be used for MRI, magnetic resonance imaging. And we can take a new spin of that using this electrical circuit. So you have to realize that coupling to a single spin, it's extremely difficult. So if you take a simple LC circuit and want to couple a single spin via the magnetic field generated by the inductor, you can take the simplest inductor that you want, just a wire, and put a spin nearby. And if you simplify the problem as lowly as possible, you can find that the typical distance, you can have only one parameter to parameterize the distance between the spin and this inductive wire. And you can calculate what is the AC magnetic field produced by the wire, and you can go back to this interaction strength between the spin and the LC circuit. So that is what is plotted here. And you can see that, well, at a 1 millimeter typical distance, you are very much below a 1 Hertz interaction strength. That's to say, if you pay a spin in an LC circuit where the typical distance is 1 millimeter, you will have to wait more than 1 second to see one swap between the spin and the LC circuit. So if you do not go to the quantum level, where we have this very long lifetime, then you will not see anything. And even if you go to this using this superconducting resonator, the lifetime is only of 10 milliseconds, so you will not see anything. So that's what I'm showing here, is that the typical scale that we need to compare this to is the lifetime of the resonator, which is approximately of tens of kilohertz if you translate it into rates. And that's defined two regions: the region of weak coupling that we are in until the distance becomes on the scale of 10 nanometer, and the area of strong coupling below a typical length of 10 nanometer. So how come we can see any kind of signal with magnetic resonance? That's the question. Because a typical usual spectrometer is very much in the millimeter scale range. And that's because the detection relies on a large number of spins that boost by a factor n squared the signal that is emitted by the spin. And so to see any kind of signal, a typical spectrometer generally relies on having 10 to the 8, 10 to the 12 spins inside the resonator. But now, with all of the techniques that we have developed for these quantum microwave circuits, we can make much more sensitive spectrometer by developing this high quality factor on very much small mode volume resonator. So this is LC resonator, that's to say an interdigitated capacitor in parallel with an inductor. So the inductor is 5 micron wide, and the spins are just below the surface with a depth of 100 nanometer. So if we put this resonator on this bar, we are a bit closer to the strong coupling regime. We are not there yet, not at all, but that still gives us a boost on the sensitivity, so that when we perform an experiment of magnetic resonance, we can show that we are able to detect approximately 12,000 spins. And we can keep going. For example, if we go to now a 500 nanometer wire, so that's the active part of the setup, then we can go and detect approximately 50 spins with a signal-to-noise ratio of unity. So that's basically what I wanted to show you, is that we can develop this high quality factor, small mode volume resonator to concentrate the magnetic field at the spin location, increase the coupling, and use that to boost the sensitivity of magnetic resonance experiment. So that concludes the second part. And the last part is about using electrical circuit. So this time, this is a superconducting circuit to test the quantum nature of phonons. So These phonons are going to be a surface acoustic wave, as the one that have attended the lecture on Monday already know. So those are Rayleigh waves. They have a longitudinal propagation. That means that for each point at the surface, when the wave is passing through, it will have an ellipsoidal motion. The wavefront is linear. It propagates on the track. And it's very well-known wave that has been mastered since the 60s, and it's used in many, many classical devices. So this is a wave. That's a really wave. That's a motion. And this is also a phonon. So a phonon is like a photon. It's a quantum object. So it should also have a wave-particle duality. So it should also be possible to treat it as a particle. So can we make a test using superconducting qubits that will test this wave-particle duality of the phonons? So how can we do that? We can go to photons and see what has been done for photons to try to answer this question. So if you want to show that a photon has a wave-particle duality, you can first check the wave property. So that can be done with an interferometer. So I've learned since I've been here that I should not forget to say it's a Michelson-Morley interferometer. You can also think of a Young double-slit interferometer. So all of that relies on the fact that you have a coherent light source that follows two paths, and any dephasing or phase difference accumulated between the two passes will result in an interference-like signal on the detector. So I wanted to be courageous and rewrite my whole presentation using this Michelson interferometer, but I'm afraid it was a bit too complicated and not very clear, so I will stick with the Mach-Zehnder interferometer. I'm very sorry, but so that's testing the wave-like interferometer, such as I've shown you, is testing the wave-like nature of the photons. Now, if we want to test the wave-particle duality, you can replace the source with a single photon source. So here in the Mach-Zehnder interferometer, you go through a beam splitter that is going to define two paths. Either the particle can go on the upper path, be reflected by a mirror, and go to a second beam splitter, or it can go on the downward path and also encounter the same beam splitter. And if you have two detectors placed after the second beam splitter, you will observe an interference pattern that is out of phase, in opposition of phase, sorry. Now, that still doesn't prove the particle-like nature of the photon. So what you can do is remove the second beam splitter. And in this case, you will see that for each experiment, either the particle went on the blue path or on the red path, and you will always detect it 50% on this detector or 50% on this other detector. But there will not be any interference. So that's basically going to a particle-like detection. Either the photon went on the blue path or on the red path. You can say, well, this is obvious. There is no recombination, so of course there's no wave-like effect. So what you can do is replace the beam splitter and then try to, during the experiment, see where is the particle going, where is the photon going. So acquiring finally the which path information. So when you do that, you will also see no interference. And so the explanation, so this works also if you do the experiment placing the beam splitter after the photon has entered the interferometer. So there's no way that the photon is a tricky thing that knows what is happening in the experiment and decide before whether it wants to be a wave or a particle. No, it's only the measurement that decide whether the photon should be described as a wave or as a particle. And so in quantum physics, we say that during the propagation of the photon, the system is in an entangled state. That is a superposition of traveling through the blue path or through the red path. And this is only when you do the measurement, either of the which path information or on the detection at the end, that you will either collapse the wave function and determine whether it was on the blue or on the red path, or that it was in a superposition state. So that's for photon. Can we do the same thing with phonon? Well, we should have a phonon track. We need a single phonon source, sorry. We need to find beam splitter, mirrors, and detectors. And that's what we have built with submitting qubits and this surface acoustic wave. So what we have done is take interdigitated transducer that can generate phonon at around 4 gigahertz on piezoelectric material lithium niobate. We have on one of the port, so this is a closed phononic track, because on each side of this transducer, we have placed phonon reflectors, meaning that any phonon that is generated by a microwave signal applied on the transducer will propagate and be reflected by these bright mirrors, and then they are able to come and re-excite the central transducer. So as the excitation source, we have picked a submitting qubit whose microwave signal can be converted into phonon by passing through a tunable coupler. So people who were there on Monday know that these tunable couplers has two uses. The first one is to be able to preserve the state that is stored inside the submitting qubit, and while the phonon is propagating. The second is that to have an efficient reception of this phonon, we need them to have a symmetric wave packet, and by slowly opening the coupler, we can put into shape this wave packet. But so that's slightly technical, and I don't want to enter into this detail. I just want to show you that, yes, indeed, with this kind of setup, we can make an efficient single phonon source receiver. So that's an example of emitting and capturing a single phonon. We start with a qubit in its excited state, and then we slowly modulate the coupler so as to release the excitation stored into the qubit, so that the emission, the decrease of excitation probability of the qubit that you see here. Then the phonon is emitted on both sides of the transducer. They propagate for 500 nanoseconds, and then we remodulate the coupler so as to capture again this excitation. And we can do that with an efficiency of 67%, and we are more or less convinced that this is mainly due to acoustic losses. So that's finally the first brick for building an interferometer with phonon, is that we have the single phonon source receiver. So now what happens if we modulate the coupler so that we only emit half of the excitation stored inside it? So what happens is that, well, only half of the excitation is emitted on the shape of phonon, so the excitation is propagating as phonon, only half of it, and half is stayed into the qubit. So in the middle, you can say that we're in a superposition of paths. Either the qubit is in the ground state and one phonon is traveling, or the qubit stayed into its excited state and there is no phonon traveling inside the track. And then what happened during the capture? Well, we can say, using input-output theory, that what is coming out of the transducer once we have done this capture operation is the sum of two contributions. What is emitted by the qubit and the phonon field that is reflected off the transducer. And there is a minus sign, so that when you do not change anything, these two contributions are actually equal in magnitude, but opposite in phase, so that they cancel each other. So there is nothing going back into the phononic track. So everything is now back into the submitting qubits. So that's why you see, even if you emit only half a phonon, you will recover the full excitation of the qubit at the end. So here, there is no, we don't go back to 1 because of the acoustic losses. But what we can, so to implement the interferometer, what we can do is apply a dephasing pulse during the phonon propagation. So if we change the frequency of the qubit during a slight amount of time, we'll create a dephasing between the qubit and the phonon that is traveling. So basically, we are going to introduce a phase on the qubit field with respect to the phonon field that is traveling through the track. So now if we try to capture again the qubit, and for example, have engineered a pi phase, we see that the qubit completely emits its field, because then this contribution is in phase with the phonon reflective of the transducer, and the interference is constructive instead of destructive. So we can perform this experiment for any kind of phase, and we see that the final excitation of the qubit has indeed this interference-like pattern. So with that, I hope I've convinced you that we have built a phonon interferometer. So now the question is, well, is that so that's for sure showing that the phonon is a wave, but can we also show that this behaves as a particle? So one thing that we should do is capture the which pass information. So how can we do that in our system? So I wanted to simplify what is coming next. I'm plotting this interferometer as a Mach-Zehnder interferometer, but it's a bit particular. The beam splitter is actually the half emission operation I do. Then the two paths are actually whether the excitation stayed inside the qubit or whether it went inside the phononic channel. And the second beam splitter is actually the capture operation. And I can only record one of the two paths using the qubit. I don't have any detector on the phononic track. So now if I want to detect what is the which pass information, well, I have to be a bit sneaky and I can look at the qubit. So I want to look at the qubit, but I do not want to disturb the superposition state that is on the two ground level of the qubit. So I have to play with the third state of the qubit. So I apply a microwave pulse that is tuned to this transition frequency, so as to take the excited state, bring it to the second excited state that we call the F state, and I can't just stay there. I need to go back to the excited state while capturing the information that I was in the excited state, so as to be able to still have this beam splitter operation not disturb and go back to the initial interference. So to do that, we trigger the emission of a phonon from the F to E transition, so that we have actually generated a second phonon only if the qubit was in the excited state when we look at this time t. So this means that the state of the system, which was actually a superposition of whether the excitation was in the orange or the blue path, is now also correlated with the existence of this second phonon. The second phonon exists only if the qubit was in the excited state during the phonon propagation. So this is the which pass information. If the second phonon exists, then it was this path that was followed. So if I do that, I should project the interference, and that's what we observe. When we do this experiment with this additional pulse and emission of a second phonon, we collapse any kind of interference signal. So now, in quantum mechanics, we can be a bit more, we can try to see if we can't recover these interferences in some way. So that's called the quantum eraser test. So, that was proposed by Scully and Joule in 1982. And the question is it possible to erase the knowledge that we have gained on the system and recover the interferences? Can you undo what you have done? Can you undo the fact that you have looked at the interferometer and acquired the which path information? And basically, for us, very simply, it is, can we undo the existence of that? Can we erase this second phonon that we have generated? Well, it is possible to do that. And for that, I have to use the second qubit that I have not mentioned so far, but that is connected to the other electrode of the transducer, so which can capture any kind of phonon that is propagating through the signal, and in particular this green phonon. So what we are going to do is perform the interferometry, acquire the which path information by triggering the emission of this green phonon, capture it by qubit 2, and this has changed nothing. It's just that now that I capture it with qubit 2, I can actually detect this which path information. But I haven't erased it. So what I can do is now apply a pi/2 pulse on the qubit 2, so that you see that when I capture this qubit here, I take the qubit 2 to its excited state, whereas when there is the excitation is actually in the phononic path, the qubit 2 is in the ground state. So basically, I've changed the existence, the encoding of the which path information on whether the second phonon, the green phonon, existed, to whether qubit 2 is in its ground or its excited state. So now, if I apply a pi/2 pulse to mix this population, well, I will have erased everything. It's like I have done nothing. And now if I post-select the result of the measurement on Q2 being in the excited state, I should be able to erase this which path information and recover the interferences. And so that's what we see in our experiment. When we do this capture of the second phonon, apply this pi/2 pulse, then we recover the interferences. So because we have these acoustic losses, we do not recover the entirety of this green phonon, and so we cannot recover the full interferences. So this is a test using superconducting qubits that we can manipulate phonon and really use them as quantum objects. So that's kind of conclude what I wanted to show you, and I've tried to illustrate that using quantum circuits, we can probe other solid-state quantum system. We can probe for material properties, and so it's a great tool for quantum sensing, in my humble opinion. So that's basically the end of the colloquium. I just wanted to finish by acknowledging all the people that have contributed to this work. So all the phononic part was done at the University of Chicago in the Cleland group, and the coupling to spins was done in the quantomics group at the CA Saclay near Paris. And thank you very much for attending to this talk.
So I guess we have some time for questions. Josh.
Analogies for acoustic losses in phonons to the in photons, like the equivalent type of losses in photons as well? Or is that only something you see in a phononic system?
So do you mean that the acoustic losses here are, I mean, if you look at the equation, they go in the same way. But we have acoustic losses because of the surface acoustic wave that we are using, that they are scattering when propagating along the surface. So the origin of the losses are different, but they go in the same way during the equation, yes.
So when you make that measurement in the interferometer using the second phonon, so at that point you collapse your wave function. So how does adding a phonon or exciting the other Q2 using another phonon, how does that restore the original wave?
So I actually do not collapse the state until I measured it. So basically, this is the state of the system, right? You see, this is how you write it. On one side, I have either the qubit in its excited state and a phonon traveling, and that means that there is no second phonon. Or I have the qubit in the excited state, no traveling phonon, and this additional phonon, since the qubit is in its excited state. Now, when I'm capturing the second phonon, I'm just changing this state to the 0 being the qubit 2 in the ground state, and the 1 into qubit 2 being in the excited state. So I have not collapsed anything. It's only when I'm going to measure qubit 2 or qubit 1 that this is going to be collapsed. And by applying a pi/2 pulse on qubit 2, that's where the equality comes from, and that's where I can recover the interference when I detect qubit 2.
So in the second part of your talk, you showed us how we can go from
10 to the 12 spins to just a few hundred. Is there any possibility to go beyond, down to maybe even 1 spin, or?
Well, then that would be going to the 10 nanometer scale, so having 1 spin located 10 nanometer away from the nanowire, and that's one of the projects that is actively pursued at the quantomics group in Saclay, yes. Yeah.
And that would become, the physics would become very different now because you don't have an ensemble anymore.
Yes, that will be a single quantum object that is probed, so the physics is quite different, yes.
So the second
phonon, what I understood, needs to match your second excited, first excited state energy difference in the junction.
Yes.
So, but you have all these phonons with the different frequencies available in the same system, and you can move at different time possibly, and therefore complicate the experiments.
So I've a bit simplified the experiment. So what we do is, when we want to generate this second phonon, is that we tune the frequency of the spinning qubit so that this transition is actually at the same frequency of the transition on which the first phonon was emitted. So basically, we keep for phonon the same frequency, or the same frequency range. We modify the flux threaded through the squid. We modify the flux threaded through the squid of the superconducting qubit to change the superconducting qubit frequency.
So you made it with 3 people, but then you are in the same problem. How do you know that you excite one or the other? Because you start out with saying when you get harmonic potential, so harmonic to expose that. But now you tell me you make in the same space.
No. I'm not saying I did them the same spacing. I'm just, maybe I'm going to draw it. It's going to be easier. So, I have the qubit first frequency, right? And then that's the second transition frequency. So at the beginning, I'm keeping this frequency constant, right? To emit the first phonon, sorry. Then it's traveling, and I want to test that the qubit is in excited state. So that's where I generate the second phonon. But I want the second phonon to have the same frequency as this one. So what I do is I change the flux through the squid to modify the transition. But when I do that, to bring this transition to the same frequency as this one is also modified. Then I emit the second phonon, and then I want to capture this one back again. So then I bring back the frequency to what they should be to do the capture of this phonon. And this one is emitted as this frequency, and qubit 2, it doesn't matter. I just match it to this frequency to capture it. So when you look at the actual pulse sequence, it's a bit crazy and going into all the directions.
Okay. So as far as I know, a lot of the developing computers that, say, Google are using use microwave photons. Is there a distinct advantage to shift these phonons and these acoustic waves rather than photonic phase?
So you mean, would it be useful to use phonon for for quantum computing? Well, you can see that the acoustic losses are pretty high. We have only 70% efficiencies in all the processes that we do, so that's already a big hurdle to overcome if you wanted really to use the phonon as a quantum object into which we could encode the quantum information. Superconducting qubit, the comparative number is more like 99%, so that's not at all the same scale. But yeah, I mean, why not? Maybe we could find a very good mechanical system where, yes, the phonon would be long-lived. But then the question is, can we have the same type of nonlinearity that we have with the Josephson junction? Well, that I don't know. That has yet to be invented.
Okay, but I have many questions, but I'm instead going to make a comment, which is perhaps Charles Bennett, who was a pioneer in this field, and he used to like to say about how inaccessible quantum phenomena are. So he would begin his talks by saying, when I was driving down the Merritt Parkway this morning, I was struck by the complete absence of quantum phenomena. But in this case, I mean, here you're seeing these really subtle quantum effects in circuits and surface waves. It's really quite extraordinary. So thank you very much for another great talk, and we look forward to the remaining seminar tomorrow at 12:45.